before we go on and see how this corresponds to the reference circle model, let's just recapitulate. Now, for any simple harmonic motion is what happens anytime you have a restoring force that's proportional to your distance from equilibrium. A minute ago we saw that the restoring force was negative mg over L times x, your distance from equilibrium. Earlier in the course we saw that for a spring, well, we actually modeled it for rubber band, and it wasn't a perfect model for a rubber band. We still got a pretty good model where the force was negative k times the distance from equilibrium, where k was a constant that we could measure just by doing the slope of the force versus position line. And now, if we have this kind of a restoring force, where we have a force back toward equilibrium, negative k times the distance from equilibrium, or the displacement from equilibrium. Remember that force is mass times acceleration, and as we just saw, acceleration is a second derivative of your position function. So it's mass times the second derivative of position equals negative kx. Again, we're talking a little calculus here. Everybody needs to know the results of this. Calculus people, of course, calculus-based students, need to know all the details. So here are some of the details. When we have the conditions that we just described, the restoring force with restoring force constant, a possible solution is x of t equals a cosine square root of k over mt. And it turns out that this is really the most general solution if we just add a little phase angle at the beginning, and we'll talk about that later on. But this is a solution of that equation, and we get this just the same way we did when we had the square root of g over L involved in it. So that for a pendulum, your f is negative mgx over L, which is negative mg over L. Now that's an f equals negative kx with k equal to mg over L. So we say k for a pendulum is just mg over L, and there's your force constant for the pendulum. And square root of k over m, of course, is the constant that we get up here, and for a pendulum we work that out and we find out that that's just the square root of g over L. Now we want to look at the significance of this term, so we look at the reference circle model. You just saw the pendulum going back and forth and keeping pace with a point that was moving around the reference circle, keeping pace with its x-coordinate. What is the x-coordinate of a point on a reference circle? Well, if the point is at angle theta, then the x-coordinate is a cosine theta, just by definitions of trigonometric functions. Think of this as a vector of length a being the radius of the circle, so it has to have length a if it goes from the center out to the rim. And this vector is then going to have an x component a cosine theta and a y component a sine theta. So we're just really, when we follow this vertical line back and forth, we're following the x component of this vector back and forth. And we say that the angle theta is the square root of k over m then. And that's wrong, it should be k over m times t. Got a bad angle here. See if I can write a half decent t. That's about all we did, is half decent. And for a pendulum, that would be g over L times t, with the t outside the square root. And that's a little harder to pin in there. Okay? The point, though, is that this theta here is just obtained by the square root of k over m times t. And this tells you the angular velocity around the circle. And if you recall angular velocity from our recent study of rotational motion, you'll understand exactly what this means. Square root of k over m is, or square root of g over L in the case of a pendulum, is the angular velocity with which the point around the reference circle moves in order to model the pendulum. And we say then, if this is our model, then the circle is the model. Theta is the square root of k over mt, which is omega t. Omega is the square root of k over m, or the square root of g over L. And omega is what we call the angular frequency when we put it in the equation here, or the angular velocity if we talk about how fast the point moves around this reference circle. Okay, so there's your model, basic model of simple harmonic motion, especially applicable to a pendulum. And we used the x-coordinate when we talked about the pendulum because the pendulum was moving back and forth, and that's where the x-coordinate usually is in the horizontal direction, which is the direction of motion of the pendulum. Now if we take the observation we made in class that omega, for the not for the pendulum that you observed on the video clip, but for a pendulum that we observed in class, we adjusted the angular velocity until we came to 2.65 radians per second. And then we calculated the square root of g over L. Well, we didn't calculate the square root of g over L. We noticed that omega is the square root of g over L. And we can solve this for L. Then, knowing omega and certainly knowing g, we could find the length of the pendulum. And we got g over omega squared, which came out 9.8 meters per second squared over the square root of 2.65 radians per second. And that all came out to 1.40 meters. And that's exactly what we got when we measured the length of the pendulum. We didn't know in advance. We predicted it by fine-tuning this angular frequency. And from that, we were able to accurately predict the length of the pendulum.